Hello everyone, I'm Dian Wang from Northeastern University. Today I'm very excited to talk about our recent findings on the surprising effectiveness of equivariant models in domains with only latent or implicit symmetry. This is a joint work with John Park, Neil Salter, Lawson Wang, Robin Waters, and Robert Platt. Recently, there have been a lot of success in using equivariant models in the machine learning community. Equivariant models have shown to be very effective in many domains, like computer vision, molecular representation, trajectory prediction, robotics, and so on. Equivariance can represent the symmetry in a function. In an equivariant function, when the input is transformed by some transformation g, the output will be transformed accordingly. When we have symmetry in the problem, we can enforce the symmetry using an equivariant neural network architecture so that the sample efficiency and generalization are greatly improved. For example, in this two-dimensional position estimation task, where the goal for the network is to estimate the position of the duck, we can use an equivariant network that's equivalent to SO2 rotation so that the network can automatically generalize to all of the rotated versions of the same state. However, one of the main constraints of equivariant models is that they require a well-defined input transformation. In our example, that means we will need a perfect top-down image so that we can use the rotation of the image to represent the rotation of the state. However, real-world images are not always that perfect. There might be a fixed background that will not rotate, or we don't have access to a top-down camera. This is very common in real-world tasks. On the left, I have an example in robotic manipulation, where a perfect top-down camera might only exist in a simulator. In the real world, because of the occlusion of the arm, we might need to use a side view camera instead. On the right, I have an example of jet flow data where we have some flip invariance property. However, there are some noises that might break such equivariance. In such a scenario, there will be a mismatch between the problem symmetry and the model symmetry. In other words, the object transformation will be different from the image transformation. In such a case, it will be hard to find an equivariant network that perfectly models the object-wise symmetry. However, we can still use an equivariant network to model the image-wise symmetry. In this work, we found out that modeling the image-wise symmetry is actually very helpful for the model to learn the object-wise symmetry. We call this extrinsic equivariance. It is extrinsic because the rotated image will never be seen during training or testing, and we are enforcing equivariance towards out-of-distribution data. Concretely, in this work, we make two major contributions. First, we define three different relationships between problem symmetry and model symmetry. We call them correct, incorrect, and extrinsic equivariance. Correct equivariance is when the model symmetry matches the problem symmetry. Incorrect equivariance is when the model symmetry conflicts with the problem symmetry. And extrinsic equivariance is when the model symmetry will transform the data to out-of-distribution. We further demonstrate that incorrect equivariance will lead to some inevitable error, but extrinsic equivariance can actually be very beneficial. To better illustrate our idea, I will first introduce correct, incorrect, and extrinsic equivariance using a binary classification example. Here, our goal is to classify the blue and orange data living on R2. We want to find the hyperplane that separates them. The gray region means the data distribution. Now let's imagine there's some structure of the data, where the data distribution forms a circle. Since there's some structure of the data, we can consider using an equivariant network to solve the task. First, let's imagine an equivariant network that's invariant to vertical flip. We show the group transform data under vertical flip in crosses. If we compare the crosses with the circles, which is the original data, we will see that their colors perfectly match. That means the symmetry in the model agrees with the symmetry in the problem. We call this correct equivariance, and this is also the case where people normally use equivariant networks in. Now let's imagine a different type of invariance, pi rotation invariance. If we compare the data under pi rotation with the original data, we will see that their colors are different. That means the symmetry in the model conflicts with the symmetry in the problem. In fact, If you use a network that's invariant to pi rotation in the task, you can only get up to 50% success rate, because the network will assign the same output for each pair of pi rotated data. But in the ground truth function, their labels are different. We call this incorrect equivariance, because the model is maintaining an incorrect symmetry that will lead to higher error. It is easy to imagine what will happen under correct or incorrect equivariance, but there is actually a third scenario that's in between. What if we enforce scaling invariance? Now, under scaling, the group transform data will be out of the input distribution, as is shown in the gray ring. Even though there is still some mismatch between the problem symmetry and the model symmetry, but this time it will not lead to any error, because the group transform data are out of distribution. So we call it extrinsic equivariance. In fact, we hypothesize that extrinsic equivariance can make it easier for the network to generate decision boundary. Recall that in the image space, the rotated objects are in distribution, but the rotated images are out of distribution. So if we use a rotational equivariant network here, we will have extrinsic equivariance. To validate our hypothesis that extrinsic equivariance is helpful, we first perform an experiment in a supervised learning setting. Here, our goal for the network is to estimate the relative object rotation between two inputs. If we have a perfect top-down image, then we will have correct equivariance. However, we introduce some symmetry breaking factors that will lead to extrinsic equivariance. We call them symmetry corruptions. Under each of the symmetry corruption, we compare the performance of an extrinsic equivariant network shown in blue versus an unconstrained CNN shown in green. The x-axis shows the number of data in the training set, and the y-axis shows the test accuracy after convergence. As we can see in the plots, under each of different symmetry corruptions, the extrinsic equivariant network always outperforms unconstrained CNN. We further equip the unconstrained CNN with data commutation, where the data commutation will also achieve equivariance, but not through weight sharing. If we compare the data commutation baseline in red with the extrinsic equivariant network in blue, we will see that they have similar performance, meaning that the key success to the blue line is the extrinsic equivariance. We further perform another experiment in reinforcement learning in robotics. Here, we compare the performance of an equivariant actor credit algorithm with some baselines, but we use a side view camera angle instead of a top-down camera angle. The side view camera will make the equivariance extrinsic. Comparing the equivariant actor credit algorithm in blue with a baseline in other colors, we will see that there is a significant improvement using the equivariant actor credit, even though the equivariance is extrinsic. But why does extrinsic equivariance work? First, the symmetry mismatch only exists on the input of the network, but not on the output. We always know a priori about the group action on the output space. This is an important inductive bias that can still aid learning. Second, the image transformation might be visually very similar as object transformation, so the network will only need to learn the mapping between them. This significantly reduces the learning complexity. Although we have some hypotheses, a major limitation of our work is that we don't have a theoretical explanation of why extrinsic equivariance is beneficial, and we will leave it for the future work. To sum up, we make two major contributions. First, we define correct, incorrect, and extrinsic equivariance. We also demonstrate experimentally that extrinsic equivariance can be very helpful. In extrinsic equivariance, we are adding an inductive bias that does not perfectly match the data. One might expect this is problematic because there is a symmetry mismatch. However, in practice, we show that it's very useful. We believe our work significantly broadens where an equivariant network can be applied. For more information, please visit our website or scan the barcode below. Thank you.